Hello, I'd like to talk about a use of the stack that you use every time you program and don't realize you're using the stack. Uh, to understand this, when a program, pardon me, when a program is put into memory, the loader allocates it memory. We don't have to think about this when we look at our C++ Visual Studio because it's done automatically when you do the Control F5. But it's useful to know, in case you're writing more advanced programs, just how this is done. The point is that when we load the program, there isn't one piece of memory. No, I should put it this way. We get a block of memory. We don't get all of the memory because most computers would be wasting them if we only put one program in them. So we're sharing the memory with other programs. The operating system takes our program and finds a place for it if possible, and then the loader puts it in that place. Now, the way it does it is it takes the block and we have 5 segments of our program in the block. And I think the best way, the first one is we have the code that has been translated into an assembly, probably a machine language. This is done by a program called the compiler. Again, you don't see that when you are running Visual Studio. As an aside, when you do Python, you do not have a compiler. Python is an interpreted language, and it translates it line by line rather than all at once. But when you use Visual C++, the compiler looks at our code, finds out what errors are in there, and then if there are no errors, it creates a translation into something that can be loaded into the computer. Now, along the way, there's a language called the assembly language, which is sort of very close to the machine language, but not exactly the machine language. You'll look a little bit at assembly language when you do computer architecture. So we are ready to put our program in. Now, what do we get? This segment is the code. It is called the text segment. This is an area that is never supposed to be written into in your program. Once you put the text in, you're not supposed to change it. That is a thing that was not there in the beginning of computers. You used to be able to write over your text, and that caused horrible problems, lots of debugging. But they basically have changed that. The text is something you're not supposed to change. Now, the second part you get a data section. This is where the initialized variables are stored. So all the places that you gave names to and put values in, they belong in here. It's separate from the text because you can write into the data section, but you can't write into the text section. Complicate matters, you also get a ESS section, and this is called something like block started by symbol. I don't think 1 out of 100 programmers know what that means. I looked it up. It comes from an old computer. This is where uninitialized data is placed. It's still part of your data. You're still going to use it, but it starts off with you didn't put values into it. The computer does. The computer initializes these variables to 0. And that can be a bad situation sometimes because it doesn't take care of the worrying about what kind of variable you have. So these 3 sections are always there. Now the next 2 sections, the rest of this block, and it comes in 2 pieces. Above the DSS, you get an area of free memory called the heap. There's a heap sort that you may see next semester. It has nothing to do with this. The heap is just a fancy name for a mess of empty space. When we call new to create a variable, the space for it comes from the heap. Now, you might not catch an important point here. The heap is finite. It's possible you could run out of room. If you do a lot of allocation, you wouldn't have any room left, and you'll get some kind of an error message. The heap is, I've not had too much trouble with it, but that is possible. But there's another section in here. Above the heap is a stack. And this is exactly what you have been told a stack is as we've been talking about it. This stack is used to call and return from functions. Every program has to have it. Every time you call a function, stack is involved. When you call a function, the return pointer, when you call a function, the address to return to is placed in the stack. So when the program finishes, it'll know how to return. It'll know where to return. Variables called by value are copied into the stack. Variables called by reference have a pointer to them in the stack. Now you notice we also have introduced that word you like so well, pointer. It's a use for the pointer. So this means that every time you call a function, you're putting things inside the stack. This is why recursion can be difficult, because every call of the recursive function builds up some more in the stack. So this is, it just happens. It's there. Every time you have a program, you have a stack. So what I'm saying is stacks are very important to programming. Now, there's a picture of how this all goes together. Let me move it down a little. Remember that items in the memory are numbered. They're numbered from 0 up to whatever the size of the memory is. And when you go in, when your program goes in, it gets a starting address for its block. It gets what the first piece of code is supposed to go. Where is it going? It gets this address. The loader then puts the text in there. When it finishes putting the text in, it puts the data in there. Numbers are growing. They're getting larger as we go up. Then the BSS segment, and then there's an interesting item that's done for the rest of it. The heap and the stack occupy the same part of memory. That's because we don't know which one will need the most, and we'd like to be very efficient and fix it so that if the stack needs more and the heap doesn't, it can use more of this. And if the heap needs a lot and the stack doesn't, the heap can use more of this. But they grow in opposite directions. As you put things in the heap, the numbers grow larger. As you put things in the stack, the numbers get smaller. This is all taken care of by the way the program in machine language actually handles the stack and the heap. It's an interesting setup. It has to, we need this because basically we need to be able to get to programs, to functions. And this is the way. This is how we do it. Now that's all I want to say at this point about stacks. I think we have finally finished stacks. You have a homework on stacks. And the next topic we're going to talk about is queues. And hopefully I'll have that out very shortly. So thank you.